Welcome back, everyone. The second talk of today will be given by Robert Kropholler from Minster University, and he'll be talking about groups of type F2 over fields, but not over Z.
Great. Thank you so much for the invitation, and thank you all very much for coming. So yeah, I want to talk about groups that are of type FP2 over fields, but not over the integers. And so I'm going to define what FP2 is and tell you sort of the background. Okay, so let me start with a definition that is going to be my definition of finitely generated and finitely presented. And so you haven't seen these before. It's an exercise to, if you get a moment, think about why they're equivalent to whatever definition you use. So group G is finitely generated if it acts properly co-compactly on a connected CW complex. Okay, so I mean, this is sort of easy to see. So for one direction, I mean, basically, you should think of this CW complex as just being the Cayley graph, right? So if your group is finitely generated, then this action is free, it's proper, and it has finitely many, it has one orbit of vertices and finitely many orbits of edges, okay? And if you have a space that with this action, then you can somehow use that to, you can sort of see the Cayley graph as being very close to the one skeleton of that space. And so finitely presented has a similar thing, which is that it's the same thing. So if it acts properly and co-compactly on a CW complex such that instead of now requesting that it's connected, request that pi1 is trivial. Okay, so you could think about this first one as saying something like pi0. So this CW complex should be x, right? And you could think about this first one as saying pi0 of x is trivial, or and so once again, you should think about why this is equivalent, but it's really sort of building the Cayley 2 complex or somehow using some co-compact action to get out a finite presentation. And so these are sort of two properties that hopefully we're all very familiar with. I think I'm talking to a room primarily of geometric group theorists, so hopefully everyone should be happy with finite generation and finite presentability. And these were the first in a line of a sequence of finiteness properties defined, I guess, by Wall. So you can sort of generalize these, and there's an obvious way to do it. So you could say, well, if there exists a CW complex X with a proper co-compact G action such that pi I of X is trivial for all I less than n. Okay, so right, so you sort of seen that this definition gives you that F1 is equivalent to finitely generated and F2 is equivalent to finitely presented. And so these sort of higher finiteness, these sort of Fn you should think of as sort of generalizations of finitely generated and finitely presented to, say, higher dimensions. Okay, and so now, you've taken your, so if you're taking your first course in algebraic topology, the first things you meet are the fundamental group. Right? I mean, when you take a first course in topology, you meet connected spaces, then you meet the fundamental group. The next thing you meet isn't usually the higher homotopy groups. So in fact, the next thing you usually meet is the homology groups. So we can do, so instead of requesting these homotopy groups vanish, we could do the same thing where we say that, I see. So I've decided to change from my previously prepared notes, which is foolish, but we're going to go with it. So you could do the same thing where you say you have a proper co-compact GCW complex or I'm just going to say G complex X. And instead of requesting that the homotopy groups vanish for all I, you could request that the homology groups vanish. And I'm going to say sort of very obviously that I mean homology with coefficients in Z. Okay, so for all I less than n. Right, and once you meet homotopy groups, I mean, once you get to a point where you've met homotopy groups, you meet the Hurewicz theorem. And so this tells you that the first non-trivial homology group is isomorphic to the abelianization of the first non-trivial homotopy group. And so in particular, one thing that you can deduce from this is that Fn implies Fhn, right? So if your homotopy groups vanish, then indeed your homology groups vanish. Okay, and so now you could think about perhaps, perhaps this is in some notion, homotopy groups are very topological invariant and homology groups are sort of more of an algebraic invariant. And so then you could go the full way and just sort of perhaps forget the topology of this complex and just look at the algebra that you're getting from these things. And so using that, we define Fpn. And so Fpn is just a purely algebraic statement. So if there exists a projective resolution if there exists finitely generated projective ZG modules Pi and an exact sequence zero maps to Z. So here I have P0, P1, all the way up to P, Pn. Okay, and so you'll note that there's no zero on the left. Okay, and so this is sort of taking, I mean, what you think that you've done is you've started with a complex with trivial homology, and you're looking at, say, the cellular chain complex of that complex. Now, if you have a free GCW complex, then the cellular chain modules become free ZG modules, and saying that the homology vanishes says that the augmented chain complex has trivial homology. Sorry, it tells you that the augmented chain complex is exact up to the point where homology vanishes. Okay, so this statement that I've written at the top, right? So Fhn implies Fpn, right? And so you should think of Fpn as sort of a pure algebraization of the Fhn property. Okay, you're just forgetting the topology of the complex. Okay, so a couple of right. So these are the definitions and these are the things I want to talk about. And so hopefully you've sort of met finitely presented before, and so these are sort of natural generalizations in some sense of finitely presented. Okay, and so I've given you some implications between these conditions, and there are some extra ones that are maybe less obvious, but I'm just going to state. So firstly, right, we have this one that Fn implies Fhn implies Fpn. We also have that in the sort of lowest dimensional case where these things are interesting, that F1 is actually equivalent to Fp1, right? So this is equivalent to finitely generated. Right, so in dimension 1, these properties are actually equivalent. Having this projective resolution actually tells you that you can build a complex. Okay, and similarly, the obstruction to being able to build a complex is in fact being finitely presented. So if you're Fpn and finitely presented, then in fact you are of type Fn. So once you know that you have a simply connected complex with a nice action, and you know you have this projective resolution, you can put these two pieces of information together and actually build a complex with a nice action. So somehow you're taking this algebra and you're using it to build a complex. And the last one I want to mention, just in case I slip up and later forget this. So In the two-dimensional case, these properties FP2 and FH2 are equivalent. So if I give you a projective resolution, you can actually build a complex where the first homology group is trivial from that resolution. And for higher dimensions, this isn't known. This is so the reason you can do this in dimension 2 is that when you look at the first homology, the point is that first homology is generated by loops in your space. So somehow you can think about first homology as being some sort of topological thing. But for higher dimensions, and so then you want to cone off these loops, and you can do this by adding in disks. But for higher dimensions, homology classes are represented by more complicated objects. And so say in dimension 2, they're surfaces. And so you can't glue a disk in with boundary a surface. And so it's not clear how you would build such a complex. And so it's an open question whether FPN implies FHN for n greater than 2. So somehow you get stuck somewhere. But once again, you know that this obstruction disappears once you're finitely presented. Okay, so these are how all of these properties sort of interweave together. And perhaps the first question that, well, given that I said this is open question, well, one thing that you should ask is, well, you have FP2, and I've sort of tried to tell you that this is like you took finitely presented and you first relaxed from homotopy to homology, and then you relaxed from homology to projective resolution. I told you, and I'm telling you that last relaxation doesn't actually change anything. But what about that first one? Is this property of type FP2 really are there really groups of type FP2 which aren't finitely presented? Or have I in fact just told you something which is a different definition of finitely presented? The answer is no. The answer is that these groups really exist. And the first place where these groups were found was in work of Bestvina and Brady. So sort of impossible for me to give a talk about groups of type FP2 without mentioning the Bestvina-Brady theorem. So they proved that there exist groups of type FP2 that are not finitely presented. Not finitely presented. So they're not F2. Okay, and so they found them as subgroups of rags, and I'm going to talk a little bit about their construction later. And I'm going to sort of tell you exactly what they proved, but for now, I just want to leave it as that. So these groups do exist. And in fact, the first theorem of mine that I want to mention just in passing is that, in fact, not only do these things exist, but you can even find them inside hyperbolic groups. So there exist subgroups of hyperbolic groups that are FP2, but not finitely presented. Okay, so somehow even in a world of, right, we study the world of hyperbolic groups. Hyperbolic groups are lovely. They satisfy many, many lovely properties. A very big open question, at least in my mind, is, well, what do the subgroups of hyperbolic groups look like? And the answer is that we really don't know, right? We know that there are some hyperbolic examples, but finding non-hyperbolic subgroups of hyperbolic groups is sort of a very difficult problem. And so one thing, it turns out that you can find these sort of weird, almost finitely presented groups of type FP2, but they're not finitely presented inside hyperbolic groups. Okay, so Bestvina and Brady showed that these groups exist. They showed that there's a difference between the class of groups of type FP2 and finitely presented. And then sort of more recently, right, there's this, as I say, there's my work showing that you can find these things in hyperbolic groups. But in fact, there's this remarkable work of Ian Leary, which says that not only do these things exist, but actually there are many of them. So in 2018, right, so this was published in 2018, Ian showed that, in fact, there exists uncountably many uncountably many groups of type FP2. Right, and in fact, even more, I don't know, this is startling to me, but in fact, every countable group embeds in a group of type FP2. Okay, so there are many, many groups of type FP2. And so you could counteract this with, so sort of if you've never thought about it before, you should note that there are only countably many finite presentations. So in particular, there can only be countably many finitely presented groups. Right? Each one has a presentation. There's some equivalence on this class of presentations. So not only do these groups of type FP2 exist, actually there are there are lots of them, and in some sense, you know, the ones that aren't finitely presented is really the norm. Most groups of type FP2 are not finitely presented. Okay, so this was sort of, you know, this class that, so maybe in the 1980s, it was an open question whether FP2 and finitely presented are the same thing. In the late 90s, Bestvina and Brady showed that these things are really different. And in the 2010s, Ian Leary came along and showed, well, actually, one of these classes is much, much larger than the other one. And so then in 2020, in joint work with Ian and Ignat Soroku, we showed that not only can you do this for isomorphism classes, but in fact, you can also do this in some sort of geometric sense. So we showed that there exist uncountably many quasi-isometry classes of groups of type FP2. Okay, so Ian showed that up to isomorphism, there are many, many of these groups. There's a weaker notion of equivalence that I'm not going to go into, but hopefully many of you have met before, which is quasi-isometry, and you still have uncountably many classes even in this weaker sense.
Rob, there's a question in the chat. Does the second statement, and by that is meant every countable group embeds, imply the first?
So it okay, so it does once you know that there are uncountably many finitely generated groups, right? So this comment of Colin Reed is, so there are, if you have a countable group, it has only countably many finitely generated subgroups. So in particular, within the class of finitely presented groups, there are only countably many finitely generated subgroups, but there are uncountably many finitely generated groups. So that tells you that that's going to give you an uncountability result. But I guess you need to know an extra piece of information, which is maybe also non-trivial to prove. So maybe, yeah, so maybe it strictly doesn't imply the first, but I just think it's a sort of remarkable result. Okay, so these groups exist, they exist in abundance. They're sort of, you can find geometrically varied classes, you can find them in classes of groups that are geometrically interesting, in classes of groups we care about. And so this is all sort of amazing. I mean, at least to me. And so, okay, now I want to sort of go back to the properties I defined and give another sort of different generalization. So just recall that FH2 was that you had a free co-compact GCW complex such that the first two homology groups vanish. So it's connected, reduced zeroth homology vanishes, and the first homology group vanishes, right? And I wrote coefficients with Z And so you could replace coefficients with Z with a different ring, right? You can define homology with coefficients in any abelian group. And so we say that G is of type FP2R, FHNR, sorry, if there exists a free co-compact G complex X such that, well, let's just do the obvious thing. Instead of requesting that homology with coefficients in Z vanishes, let's request that homology with coefficients in R vanishes for all I less than N. Okay, and we can similarly define FPNR, this is type FPNR, if there exists a projective, if there exists finitely generated projective. Now, instead of ZG, we'll do RG modules PI and an exact sequence as before. Exact sequence. So once again, you should be thinking about the augmented chain complex of this complex. Okay, so given these properties FHN and FPN, you can define them over other rings, right? This is a perfectly reasonable thing to do. And then you can ask, well, how do these things fit together? How do these things fit into the picture? What's really happening here? And so once again, we have the obvious thing that, right, as I said, sort of in passing, you should be thinking of this projective resolution as maybe coming from the cellular chain complex of your space. And so, so FHNR implies FPNR, right? But also, and so I guess I should say, so, and FH2 is, right, is the same as saying FH2Z, and as I defined them earlier, FP2 is the same as saying FP2 over Z. Okay, and so it's not hard to prove that, so some observations once again. So one thing that you can prove is that FP1R implies finitely generated for any ring R. And in fact, these things are equivalent. So for FP1, there's no difference between working over the integers and working over, say, Z mod 2, where things are maybe easier. And also one advantage to working over the integers is it tells you everything. So using the universal coefficient theorem, you can see that FHN over Z implies FHN over R for any ring R. And so by tensoring resolutions, you can do the same thing for FPN. Right? So replacing these finiteness properties, so if you understand these finiteness properties over Z, then you understand them over all rings, right? If you have the finiteness property over Z, then you have it everywhere. And so the question that I want to ask is, well, what about the converse? Right? Now it's true for FP1. So if I know FP1 for over Z mod 2, then I know it over Z, right? Because both of these things are equivalent to finitely generated. This isn't true as you go higher, sadly. So the converses here are not true. Here are not true for n greater than 1. right? So this sort of one is maybe an artifact of low dimensions. And I want to just say a little word about why they're not true, because it sort of relates back to the Bestvina and Brady construction. So why not? Well, this was shown by Bestvina and Brady. So Bestvina and Brady gave examples to show this is false, to show these converses don't hold. Don't hold. And so what Bestvina and Brady did, so how does the Bestvina and Brady construction go? Well, they take as input so you take as input a flag complex L. So by flag complex here I mean so L is flag if every complete subgraph bounds a simplex. So anytime you see the one skeleton of a simplex, you see the whole simplex. Another way of saying that is every non-simplex has a non-edge. I think this is a definition going back to Warren Dix, which I particularly love. And if you haven't met flag complexes before, you might worry that this is a restriction on the topology of L, but the barycentric subdivision of any simplicial complex is a flag complex. So if you haven't met flag complexes before, just think barycentric subdivision of a simplicial complex. And that always satisfies this property. Okay, and they output a group BBL, which is a subgroup of a right-angled Artin group. So I'm not going to talk about right-angled Artin groups today, but I'm sure many of you have met them before. And what they say is that BBL is of type. Oh, I needed to say compact somewhere. Right, something better be compact. So they take in a compact flag complex L. Right, so this is a simplicial complex with finitely many cells, and they say that BBL is of type FHN over R, if and only if the homology of this finite flag complex vanishes, and only if HI of L with coefficients in R equals 0 for all I less than N. Okay, so somehow they take this finite flag complex and they build some infinite group from it, which is going to satisfy these, the finiteness properties of this infinite group are going to correspond exactly to the homological connectedness properties of your finite flag complex. Right? And so it's not hard to see from this that there are groups that are of type FHN over, say, Z mod 2 that aren't FHN over Z. So for instance, if L, for instance, if pi 1 of L is, say, Z mod 3, then BBL is FH2 over Z mod 2, not FH2 over Z. Okay, so these properties sort of differ, and you can see that they differ from this. But in fact, if you sort of think about the Bestvina-Brady construction, you can sort of prove some quite nice things about just not having to check it for Z, but being able to check it over finite fields. Okay, so here's a sort of warm-up exercise. So suppose that you have a finite CW complex or simplicial complex or flag complex, and you happen to know that the, let's just say, first homology vanishes over Z mod P for all primes P. Well, here's a question. So what can you say about the first homology with coefficients over Z? So what is this? Okay, and I should wait 10 seconds to see if anyone's going to jump out with an answer. Okay, so well, what you can say is you can deduce from this statement that actually, if you happen to know this statement for all primes P, now I spilled water on my iPad. That's never going to be good. So if you know this statement for all primes P, then actually you can deduce that H1 of X with coefficients in Z is actually equal to 0. Okay, so I mean, the point being that H1 of X with coefficients in Z is a finitely generated abelian group. So in particular, it's isomorphic to Z to the n plus some torsion. And using the universal coefficient theorem, you can see that if you look at coefficients over Z mod P, you get that this is just the tensor product. Right? And this tensor product over Z mod P is going to be, well, it's isomorphic to Z mod P to the n plus some torsion part, and tensoring over P is going to kill all of the torsion that isn't P torsion. Okay, so you're going to be left with just an understanding of this. Okay, well, if all of these groups are trivial, that's going to have to tell you that this n is trivial, and it's also going to tell you that you have no P torsion for any P. And so, in particular, this whole group is going to be trivial. Okay, so going back to the Bestvina and Brady theorem, right? They're taking a finite flag complex and they're programming this into some group. And so, in fact, if you know that the homology of this finite flag complex vanishes over Z mod P for all primes P, then in fact, you know it vanishes over Z. And so, in fact, you know the Bestvina and Brady group is a type FP2 over Z. So one thing you can conclude from this is that, so maybe this is a corollary to this sort of little lemma. So BBL is of type FP2 over Z mod P for all primes P, if and only if it's of type FP2 over Z. And there's a question, but I don't fully understand the question.
I think that was meant to be an answer to your previous question.
Oh, I see. Oh, I see. I missed it for several minutes. Okay. Yes. Yeah, exactly. So, okay. So with the Bestvina and Brady groups, you actually know that once you have this result for all primes P, you have it over Z. And then, right, this implies that you have it for, implies FP2 R for all rings R. So once you know it over all primes P, you know it over, in fact, all rings. And you might you might see this, or at least I saw this, and well, I guess I sort of thought, well, perhaps this is true more generally. And then at some point I got an email from Kevin Shrevey asking me, is this true more generally? Is it true that if I know that I'm of type FPN over Z mod P for all primes P, can I in fact deduce that I'm of type FPN over Z? And one might hope that that's true. But it turns out that that's false. So this shouldn't be a 20, it should be a 21. So the answer is that you can find groups, there exist groups of type fp2 over z mod p for all primes p, but not fp2 over z. So in fact, this sort of fact about Bestvina and Brady groups doesn't propagate into the full scenario of groups of type fp2. And in fact, moreover, given any set of primes S, there exists a group G such that G is of type fp2 over z mod p, if and only if p is in S. Right? So you can find groups which are of type fp2 over every prime, but not over the integers. But also, given any sort of sequence of primes, you can find groups that are of type fp2 over that sequence, but not but not over things that aren't in your sequence, right? And so once again, this, if you go back to Bestvina and Brady, you can sort of only successfully do this for finitely many primes. So this is sort of adding in some infinite thing. Okay, so right, so that's the result. And so what I want to tell you about is what is the construction? So how are you going to prove such a result? And maybe that's sort of the more exciting thing. And so how would one prove such a result? Well, the answer is you're going to use Morse theory, and you're going to sort of take a variation on Ian Leary's construction to give uncountably many groups. So these Bestvina and Brady groups were built with one piece of data. You were given a finite flag complex or a compact flag complex, and from that you built a group. So the construction goes as follows. We're going to build a cube complex. We build a cube complex from two pieces of data. So the first is a finite flag complex. So same thing as before, we're going to start with some finite flag complex L. Now, instead of just relying on L, what we're going to do is we're going to also take a sequence of covers. Or sorry, we're going to take a normal cover of L for every integer. So let C of L be the set of normal covers of L, and sigma is going to be some function from the integers to C of L. And what we're going to do is, from this data, we're going to build a cube complex. So maybe this is my input, is going to be these two pieces of information. So a finite flag complex and some bi-infinite sequence of covers. And the output is going to be a cube complex, which I'm going to call XL sigma. And a group GL sigma, which acts on XL sigma in some nice way. And so, right, so we have this, so we're going to have this cube complex and we're going to have this group GL sigma. And what we're going to know about this cube complex is we're going to have a Morse function on this cube complex. Okay, so, right, so there exists a Morse function on XL sigma such that we know what the ascending and descending links are, right? So if you haven't met Morse functions before, so don't worry too much, but I'm just sort of saying how you program in the covers L. And if you haven't met Morse functions before, then then this will sort of all make sense to you. So there's a Morse function, which is a function from our cube complex to the reals. And I'm going to request that if I look at the 0 skeleton, well, that's way too many brackets. The image of the 0 skeleton is contained in the integers. And so then what I show, or what this construction gives you, is that the ascending and descending link of a vertex V are exactly the cover you picked out. F sigma of V. So the ascending and descending links at height n are exactly the cover that you picked out for n. So somehow you have this cube complex and you've programmed this sequence of covers into the ascending and descending links. And the point being that you can now use this to sort of program things into your cube complex or into your group GL sigma, coming from not just one piece of information, but coming from this infinite sequence of information. And so the theorem that I show is that if you take, as long as if all of the quotients are of type FPN-R, FPN-R for all K in Z, then this group that I construct GL sigma is FPN-R if and only if HI of this cover with coefficients in R is equal to 0 for all I less than N and all but finitely many K in Z. So you can go infinitely far out, and as long as outside of some finite space, all of these homology groups vanish, so you're allowed to have them non-vanishing for some compact portion, then you're going to get FPN-R. Okay, and so as I say, this construction is allowing you to take your flag complex and not just have your flag complex, but have covers going off to infinity. And in fact, this is a generalization of Ian Leary's construction. So for those of you who are familiar with Ian's paper, Ian's paper is GL, Ian's construction is GL sigma, where sigma either picks out L or the universal cover of L. So in Ian's construction, you're only allowed two complexes, two covers, either the trivial one or the universal one. And this is sort of interpolating between them. Okay, and so here's my example. So I thought I would have less time at this point. So maybe I'll try and go through this slowly. So the example, and so to prove the theorem for type FP2, you take a Q complex, you take a 2 complex with fundamental group SL3Z. So L is a flag complex, and pi 1 of L equals SL3Z. And then I'm going to define a sequence of covers. So my cover is going to be the cover corresponding to the congruent subgroup if n is a prime, and otherwise I'm just going to take L. I'm going to take no cover at all. And so these congruent subgroups are finite index. And so for finite groups, you have type FPN over Z. Sorry, for finite groups, you have FPN over Z. So in particular, all of these quotients are FPN over R for all N and all R. Okay, so going back to my theorem, I'm now in the setting that I have this first part all set up, right? By taking finite index subgroups, I've sort of got around this worry here. And it's a fact that we know what the first homology is of congruent subgroups. So the first homology of a congruent subgroup is exactly Z mod P to the 8 for SL3Z. And so, in fact, if I put an n here, then this generalizes and you get n squared minus 1. And if you, and otherwise the homology is, yeah, sorry. So the homology of a congruent subgroup is exactly z mod p to the 8, where p is the prime that you picked in your congruent subgroup. So now what you have is, so using this, we have our desired sequence of covers. Sequence of covers, sigma n, right? So H1 of sigma n is with coefficients in Z mod P is not equal to 0 if and only if n equals P, right? So going back to my, going back to the theorem, right? I now have, so I have all of these quotients are of type Fpn over R, right? Because they're all finite groups, all of these subgroups of finite index. And I have that this homology group vanishes in dimension 1. So I'm proving my theorem for Fp2. And it vanishes for all but finitely many k, right? And when I say finitely many here, I mean there's one k which is bad, namely k equals p. Okay, and so this gives us, so we get the desired result. Okay, so okay, so I sort of rushed through that point at the end, but or maybe I didn't spend as much time on this slide as I really should have. But as I say, so the point now is that you're finding complexes with sequences of covers. Okay, and I've done this. So the example I'm giving you is for H1. And if we go back a couple of slides, you'll notice that my theorem is only for type Fp2. So I've only managed to do the two-dimensional case. And this is just sort of somehow it was lucky that we knew what the first homology of congruent subgroups are, right? It turns out that we don't really know the higher homology of congruent subgroups. So I want to sort of leave you with two questions. So I want to add a question, which I haven't been able to show, is the result true for higher n? Is the result true for n greater than 2? So namely, are there groups of type Fpn over Z mod P for all P, but not Fpn over Z for n bigger than 2? What about, and also, so I haven't defined these things in this talk, but what about n equals infinity, and what about so for those of you who are in the know, what about going off to infinity, so having Fpn for every n, or what about Fp over Z mod P for all P, but not Fp over Z, right? So I haven't defined all of these things, but I'm happy to talk to anyone who's interested another time. So this is one question. And a second question, so it turns out that all of the groups that are constructed this way, so it turns out that if you're of type Fp2 for every prime p, then all of the constructions we know actually give you Fp2 over Q. So, so the second question, maybe this is 1 and 2. So are there groups of type Fp n over z mod p for all p, but not fpn over q. Okay, so we have this. So it turns out that it's perhaps just an artifact of all of the constructions that we know, that if you're of type fpn over z mod p for all primes p, then you're actually of type fpn over q. And it's not clear to me whether this holds more generally. One thing you could try and do is, so just to say this in passing, one thing you might hope to do is find a finitely presented group which contains the rationals as a normal subgroup. And so I don't think we know how to do that. And perhaps you want to add that the quotient is of type fp2. Okay, so that's sort of the direction that you would want to go here, right? I just want to give you, so before I finish, I want to say, well, how would you prove this result for higher n? And so I can tell you exactly the ingredients you need. And so perhaps somebody in this room knows where these exist and they can just point these out, or perhaps this is something that somebody might like to think about. So what do you need to prove the result for higher n? So what you need is a flag complex. You need a flag complex L and a sequence of covers L sub k such that for infinitely many k, for infinitely many k, there exists some I less than n such that hi of lk with coefficients in z doesn't vanish, and for all but finitely many k, hi of lk with coefficients in z mod p does vanish. And finally, you need that pi1 of L modulo pi1 of LK is FPN R. Okay. And sorry, is FPN Z mod P for all primes P. So in the example of FP2, I sort of managed to get lucky and I could use finite index subgroups. So this last condition became trivial. And I also sort of in a sense got lucky in that we know what the first homology of congruent subgroups is. So somehow this is all about trying to find covers where you sort of understand the homology and it's a sequence of finite abelian groups that you really have good control over. And we just don't know how to do that in general. And so this is how you would do it for higher n, and I think that this is a very interesting question. And I think I'm going to end there. So thank you all very much for listening.
Thank you for the talk, Rob. Do we have any questions?
Yes. Hi, Robert.
Hi.
So I was wondering whether this can be also asked for the F properties, the topological ones. Right, so Fn means that you act on a space with homotopy groups that vanish up to n.
Right.
Now, if you ask Fn of R, that would be the homotopy groups tensor R vanish.
Ah, okay.
How is this related to these ring versions of Fp and Fh? It's maybe a stupid question, but I was wondering, you know. Great talk, by the way. So I couldn't think on my side question.
Thank you. No, sorry. I think that's a. Well, I guess the issue is that it doesn't necessarily make sense in dimension 1, right? Because you're tensoring a non-abelian.
But dimension 1 is always special. So dimension 1 we understand.
Yeah, and then sure. But for higher dimensions, I guess you could ask this question, and I think I don't know what the answer is. I think you'd have to. The thing is that you'd have to fix dimension 1. So the thing you're saying is going to imply. I think it's going to be very close to implying FPN. And so then once you're finitely presented, these properties become equivalent. And if you're not finitely presented, then I think there's some careful thought into what this condition would actually mean. So I'm not sure that I know that people have studied these properties, I think is maybe the answer. And so I don't know what would happen. But I think you could do a similar sort of thing.
And another stupid question is it enough to only look at finite fields and rationals? Or could there be some groups that have FPR for, I don't know, like rationals extended by √2?
Oh yeah. I think we entirely don't.
Things that happens if you take complicated rings.
I think we. Sorry. So
in general,
for general rings, we don't know, but for fields, it is enough to just study mod P and
base
Q.
fields.
So the thing is that if you somehow there's let me just say this, there's a point that if you have so if you have a ring homomorphism from R to S, then FPN over R implies FPN over S. Right, so this is why it's enough to just do it for, right, so once you know it for Z mod P and Q, you know it for all fields. But so if you had more complicated rings, and this is also why if you know it for Z, then you know it for all rings. But if you maybe had more complicated rings that weren't fields, then there could be some interesting things going on.
Yeah, Laurent thanked you in the comments. So do we have any other questions for Robert? Well, it doesn't seem like it. So let's thank Rob one more time for his nice talk. And thanks everyone for coming. And we will reconvene in 2 weeks.